Hello dear student, welcome to the session. So in this session, we are going to discuss the topic photoelectric equation from the chapter Dual Nature of Radiation and Matter. Hope you know what is photoelectric effect. What is that? Yes, it is the process of conversion of light energy to electrical energy, that is current. Okay, so how this happens? Yes, we are having a metal plate and electromagnetic radiations are allowed to fall on this metal plate. Okay, so that the electrons will get ejected from the surface of that metal plate, and these ejected electrons are accelerated by applying an accelerating potential, and these electrons which are accelerating will cause a current which is called as photoelectric current. This overall process is called as photoelectric effect, isn't it? So what is this photoelectric equation? We can call it as Einstein's photoelectric equation. So let's see what is photoelectric equation. From entrance exam point of view, this topic is very important. So before proceeding to photoelectric equation, you have to be familiar with certain terms like threshold frequency, threshold wavelength, stopping potential, work function, etc. So what do you mean by threshold frequency? It is the minimum frequency of the incident radiation for which photo emission take place. Okay, we denote threshold frequency by using the symbol nu0. So this is called threshold frequency, which is the minimum frequency of the incident radiation for which photoelectric emission take place. And corresponding to this minimum frequency, there is definitely a maximum wavelength which is denoted by lambda 0, and that can be called as the threshold wavelength. Clear? And what is the relation between threshold frequency and threshold wavelength? Yes, definitely that is C is equal to nu 0 lambda 0. Now, what do you mean by work function? It is the minimum energy needed for the electrons to get ejected from the metal surface. And we denote work function using the symbol phi 0. So that is the work function, which is the minimum energy needed by the electrons to get ejected from the metal surface. Okay. And what is the equation to find work function? It is nothing but h nu 0. Okay. In terms of threshold frequency, we have an equation to find the work function as phi 0 is equal to h nu 0. And you can write the same equation in terms of threshold wavelength as well. How will you write this? See, from this equation, you can write nu 0 is equal to c by lambda 0, right? So you can substitute for nu 0 as c by lambda 0. So that is another equation to find the work function in terms of threshold wavelength. Okay. Now let us come to photoelectric equation. See, the electrons will get ejected only if it is having a certain minimum energy which is called work function. From where do they get this energy? Of course, from the incident radiation. Okay. There are photons in the incident radiation. What are photons? Photons are packets of energy, isn't it? So, the energy of photons present in the incident radiation is partially used for ejecting the electrons from the surface of the metal plate, which is called as work function, and the remaining is utilized as the kinetic energy of the ejected photoelectrons. Okay, so energy of photons, it is denoted by h nu. The equation to find the energy of photon is nothing but h nu, where h is the Planck's constant and nu is the frequency of the incident radiation. And work function, we denote it as phi 0, and this is the maximum kinetic energy of the photoelectrons. So here you can write this equation in many forms. In place of phi 0, you can substitute the equation h nu 0, and in place of maximum kinetic energy, you can either give the substitution as half m into V max square, where m is the mass of the photoelectron and V max is the maximum velocity of the photoelectrons. Or you can write this equation in another way by giving another substitution for kinetic energy in terms of stopping potential. What do you mean by stopping potential? It is the value of reverse potential at which photoelectric emission stops. Okay. So, what is the relation between kinetic energy and stopping potential? It is very important. Kinetic energy is equal to E into Vs. This is the relation between kinetic energy and stopping potential. So, in place of Ke max, you can also give the substitution as E into Vs. So, these are the different forms of Einstein's photoelectric equation. That is all about the photoelectric equation. But using these equations, the questions can come in many ways. We have different types of questions to solve using the concept of photoelectric equation. Okay, so hope the concept is clear. Now we can explore some questions from the recent entrance examinations where you can find the application of photoelectric equation. So shall we proceed? Read the first question. A certain metallic surface is illuminated by monochromatic radiation of wavelength lambda. The stopping potential for photoelectric current for this radiation is 3V0. If the same surface is illuminated with a radiation of wavelength 2 lambda, then the stopping potential is V0. The threshold wavelength of this surface for photoelectric effect is dash lambda. So that is a JE question. It's a numerical type of question. So read the question. In this question, the given data are regarding the stopping potential and wavelength of the incident radiation, isn't it? So two cases are given. When the radiation of wavelength lambda is incident on the metal surface, then the stopping potential is 3V0. Now, on the same surface, when radiation of wavelength 2 lambda is allowed to fall, then the stopping potential is found to be V0. So, what you have to find is the threshold wavelength for that particular surface. So, here we need an equation which connects the wavelength of incident radiation and stopping potential. We can obtain that relation from Einstein's photoelectric equation. So, let's start from the photoelectric equation, which is given by H nu is equal to phi 0 plus Ke max. So, this question is regarding stopping potential. So, we can give the substitution for Ke max as E into Vs. Okay. So, we can write the equation as H nu is equal to phi 0 plus EVs. Clear. Also, this question is regarding wavelength of incident radiation. So, in place of this nu, we can substitute C by lambda and we can rewrite the equation as Hc by lambda is equal to phi 0 plus EVs. Just rearranging the equation, EVs is equal to Hc by lambda minus phi 0. So, we are going to solve this question using this relation. Okay. Now, take the first case. The first case, it is given that when lambda is the wavelength of the incident radiation, the stopping potential is found to be 3V0. So, in place of this Vs, you have to substitute 3V0 and form equation number 1. So, E into 3V0 is equal to Hc by lambda minus phi 0. Let this be equation number 1. And for the second case, it is given that when radiation of wavelength 2 lambda is incident, the stopping potential is V0. So, in place of Vs, you can substitute V0 and in place of lambda, here you will have 2 lambda. Okay. So, that is equation number 2. Now, we have to solve equation 1 and equation 2. How will you solve this equation? See, we have from equation 2, what is EV0? We have to substitute that in equation 1. Okay. So, you will get equation 1 as 3 into, for EV0, you can give substitution from equation 2, that is Hc by 2 lambda minus phi 0, and this is equal to Hc by lambda minus phi 0. So, just rewriting equation number 1. Now, just rearranging the terms, bring this Hc by lambda to LHS, you will get 3 Hc by 2 lambda minus Hc by lambda. Okay. So, if you take Hc by lambda common, you will get 3 by 2 minus 1, which is 1 by 2. So, there you will get Hc by 2 lambda. And bringing this minus 350 to the RHS, it becomes plus 350. So, in the RHS, you will have 350 minus 50, which is 250. So, from this, you can write phi 0 is equal to Hc divided by 4 lambda, isn't it? And what is phi 0? It is work function. We know the equation of work function in terms of threshold wavelength, that is hc by lambda 0, and you got it as hc by 4 lambda. Comparing these two equations, you can understand the value of lambda 0 is nothing but 4 lambda. Okay, so the value of threshold wavelength is 4 lambda. So the answer for this question is 4. The threshold wavelength is 4 times lambda. Hope the solution is clear. Shall we proceed to the next question? Read the second question. In photoelectric effect, an EM wave is incident on a metal surface and electrons are ejected from the surface. If the work function of the metal is 2.14 electron volt and stopping potential is 2 volt, what is the wavelength of the EM wave? Here the value of Hc is given. 1242 electron volt nanometer is the value to be taken for Hc. H is the Planck's constant and C is the speed of light in vacuum. So here all the data are given. Work function is given. Stopping potential is given. The value to be taken for Hc is given. What you have to find is the wavelength of the incident radiation, that is lambda. Okay. So we can start from the photoelectric equation, that is H nu is equal to phi 0 plus Ke max. Here the question is regarding the stopping potential. So in place of Ke max, we can substitute EVS, where Vs is the stopping potential. Okay. Now, what are the given data? Work function is given. It is 2.14, right? 2.14 electron volt. And what about E into Vs? That is kinetic energy, right? If we have the stopping potential as 2 volt, then EVS will be 2 electron volt, isn't it? So 2 plus 2.14, that is 4.14 electron volt is the value of energy of photon, which is H nu. But here I am going to give the substitution for nu as C by lambda, because what you have to find here is the wavelength of the incident radiation. So from here you can write lambda is equal to Hc divided by 4.14. Okay. So the value to be taken for Hc is given in this question, that is 1242 electron volt nanometer is the value of Hc and divided by 4.14. So this is going to be approximately 300 nanometer, isn't it? Here 4.14 is in electron volt itself, so no need of any unit conversion. You will obtain the value of lambda in nanometer. Okay. So the answer for this question is option C. See the third question. When light of frequency twice the threshold frequency is incident on the metal plate, the maximum velocity of emitted electron is V1. When the frequency of incident radiation is increased to 5 times the threshold value, the maximum velocity of emitted electron becomes V2. If V2 is equal to xV1, the value of x will be dash. Again a numerical question from JEE entrance examination. In this question also, we have two cases. Initially, when light of frequency twice the threshold frequency is incident on the metal plate, the maximum velocity of the photoelectron is V1. So let us create a photoelectric equation based on that statement. We have the photoelectric equation as H nu is equal to phi 0 plus Ke max. Here the question is in terms of velocity of the photoelectrons. So we can substitute for Ke max as half mv max square. Okay. And also this question, it is given that the incident radiation is having a frequency twice the threshold frequency. Okay. So in place of this nu, I am going to substitute 2 nu 0. Is that okay? Yes. So you got the first equation like this. Clear? And this particular case, what is the velocity of the emitted electron? It is given as V1. So in place of Vmax, here you can substitute V1. Okay. Now, see here, what is this H nu 0? It is nothing but phi 0, the equation of work function, isn't it? So, in place of H nu 0, you can give the substitution as phi 0. So, the equation becomes 2 phi 0 is equal to phi 0 plus half mv1 square. You can mark it as equation number 1. In the same way, you can form equation number 2 for the second case. In the second case, it is given that frequency of incident radiation is increased to 5 times the threshold value. So, in place of nu, you have to substitute phi nu 0. And at that time, What is the velocity of the emitted photoelectrons? It is v2. Okay. So here also in place of this h nu 0, we can give the substitution as phi 0. So you will get the second equation as phi y 0 is equal to phi 0 plus half mv2 square, that is equation number 2. Okay. Now from equation 1, just by rearranging the terms, see here 2 phi 0 minus phi 0 will give you phi 0. Phi 0 is equal to half mv1 square, and from equation 2 you have 5 phi 0 minus phi 0, that is 4 phi 0 is equal to half mv2 square. So that is equation 3 and equation 4. Now just do equation 3 by equation 4. What will you get? 1 by 4 is equal to v1 square by v2 square, isn't it? So from here you can write v2 square is equal to 4v1 square, or that is equal to v2 is equal to 2v1. So what is the value of x? In place of x, we have 2 over here, isn't it? v2 is equal to 2 times v1. So the value of x is 2. The answer for this question is 2. Hope it is clear. Read the fourth question. The threshold frequency of a photoelectric metal is nu 0. If light of frequency 4 nu 0 is incident on this metal, then the maximum kinetic energy of the emitted electrons will be. So here also we can start from the photoelectric equation, that is H nu is equal to phi 0 plus Ke max. Okay. So here what you have to find is the maximum kinetic energy. So we can rewrite this equation as Ke max is equal to H nu minus phi 0. Now read the question. Since we need the answer for this question in terms of threshold frequency nu 0, we can give the substitution for phi 0 as H nu 0. Okay. So we can rewrite this equation as Ke max is equal to H nu minus H nu 0. Now read the question. If light of frequency 4 nu 0 is incident on this metal, what will be the maximum kinetic energy? Okay. So when you write the equation for the second case, let it be K max dash, that is equal to, in place of this nu 0, now you have to substitute 4 nu 0. For the second case, the frequency of the incident radiation is given as 4 nu 0. So what will you get over here? Yes, 4 H nu 0 minus H nu 0. So the answer for this question is 3 H nu 0. So that is option D. So hope the concept of photoelectric effect is clear to you, and I hope now you understood how to apply the concept of photoelectric equation for solving the numericals. So practice more questions on photoelectric equation. That's all for the session. Thank you.